All right, so everyone's got something for D. All right, let's talk about this exercise here. So we're going to take this three-dimensional shape and we're going to graph it on this two-dimensional plane, but you're going to need rulers. Oh, you're the best, man. Hmm? It's what we can afford, Luke. Doesn't matter. We just need this. We just need the straight edge for now. All right, here we go. So, what I've done so far is here is your point of view. This is where you're standing. So, you are vector one. The edge of the screen is V2 to V3, and they've connected the two lines. Your 3D image is technically on the other side of this TV screen, and you're trying to figure out what would it look like through this window. Go ahead. That's a very good question, but it's going to help us graph it a little bit better. But yes, but it shouldn't matter on the distance as much as the direction of this vector. But that is a good question. I asked the same thing, but it didn't seem to matter. Um, so with that, I did graph this vector from the corner of this object to where I'm looking, and then I placed a point on this vector here. We're choosing this to be the replacement point. So what you need to do is kind of label these points around. So this would be like P2. This would be P3. This will be P4. This will be P5. This will be P6. And this will be like P7. The order of the numbers don't matter. Just give it a name and a number. What you're going to use these rulers for on what I can't really use on my side is you need to connect each vertex. Does everyone know what a vertex is? All right, each vertex or corner of the object to V1. So draw all those lines, and then we'll figure out where we're going to place our values at. So I'm going to try my best here on this end as well. I don't know if it would work. I wouldn't be able to see it. But we're going to pretend you're looking at straight lines. All right, now that we have our lines drawn, our goal is to kind of draw the points somewhere on the vertex that we think will fall somewhere on here. And to kind of help you out, I'll take this P2 point right here, and I'm going to place it, use kind of like your, well, you're going to go from here to this line, but your goal is to try to make this as straight as possible. So you can use your ruler to kind of guide yourself to that P2 point. And then you can draw the, why this line specifically? Because this is the line that P2 came from. So P2 prime has to be somewhere on this line. With your ruler, I can already kind of tell mine's a little off, so I think I'm going to redraw it. But with your ruler, try to make that as straight as possible. And what you just did is you basically just projected this edge of the 3D image to the screen now. So the 3D image is in the back. This is what you would see there. Now with that, we can kind of use these vertices here to kind of make a dotted line to kind of help guide us to figure out the rest of it. Again, we're going to pretend these are straight lines. You use the ruler. So we're connecting it to the P1 prime and the P2 prime. Again, trying to make us as straight as a line as you can with your ruler. So this is where we're at so far. All I've done is I put a point at P2 prime to make this first edge. This edge is going to help me build the rest of it. But from V2 and V3, with a ruler, make a dotted line to P1 and make a dotted line to the P2 prime. That's all we added was 4 lines. All right. You can make them solid if you want. They don't have to be dotted. Okay. So we drew all of our vertices to V1. We picked a point on that P2 line that would make it as straight as possible. And then now these dotted lines, or your straight dotted lines, will help us know exactly where the rest of the points fall. Because it's going to be where they intersect with each one. Meaning, if I look at, let's see, P6 here would then land right there. Oh, let me get my green back out. So this would be where P6 would land based off my P1 and P2. So now this is what that edge would look like right here. Be right there. And then you kind of do that with the rest of them. So then I'm going to go to P7 here, that dotted line right there. And then I'd connect those. That's what that edge would be. And then I can connect these points. I'm sure yours looks a lot better than mine, but you should now have somewhat of a rectangle. That would be the face of the 3D object right here. That's what it would be projected on. And then you kind of continue the process. So if this was P1, P4 would fall about right here. P5 is going to be in that back corner, so it'll also fall right here. So you might see something like this, where that top part of the shape is going to be really small. Right. So there's your P5s. So this top shape is going to be kind of hard to see if I'm looking at it dead on. So it might almost look like there's nothing here. And for y'all, this actually might just be straight lines here. They might all connect nicely, where mine's a little off. And so I think actually if this is done correctly, you won't even see these little top face. It'll just be one straight line almost. Or not maybe a straight line, but maybe a crooked line, but 2 line segments. And then I'm going to take that P3. See, this is P4, so P3 would fall on this one here. There you go. So I'm sure yours looks amazing. This is what mine looks like with non-straight lines. But you should basically almost see 2 rectangular faces. This is pretty much what you're going to see. You might have some there depending on your drawing. You do not have to do this part on the test, but that is how you would take a 3-dimensional figure and map it onto a 2-dimensional figure. What you need to be able to do on the test is the next part. How's everyone's figure? They come out nice and pretty looking? Lost your way? So again, the points will have to fall somewhere on the vertices, and then it has to fall with the vertice in the intersection of the other line. So basically where these intersect, that's where you know your points are going to be. So where the, what do you mean?
I think lines are like centimeter each other.
Right. That's what I have happen here. So when you're looking at a figure from 3 dimension, depending on your point of view, and according to this point of view, I'm almost not going to see the top of that part of the screen. So that's why I have these little slivers here. Because I pretty much am just going to see this portion of my 2-dimensional figure. So yes, if you're just, if you're just having this and you're not seeing anything, it makes sense that you probably won't see it. Like, I think according to the book, if you have perfect straight lines, you won't see that part at all. Mine obviously aren't perfectly straight. Go ahead. Because all three of these points are going to be on that second line. So these 3 points, the top part of the rectangle hits the top parts of the line. So these 3 points would fall here, where these 4 points fall there. Yeah, yeah. So that's what the point of this part right here is to catch the bottom of the shape, and this is to catch the top of the shape. The only thing that you have to do is I guess the part you're guessing first is that P2 point to make it as straight as possible. Then you're going from there. So if this wasn't straight, it could, curve the rest of it. Yes, sir. Sure. Yeah. Any other questions there? Those are good ones. And again, I'm not going to expect you to be able to draw this, but I need you to understand the math that we're doing. We're taking a three-dimensional shape and we're trying to make it become a two-dimensional shape. So the three-dimensional shape that you see definitely gets skewed by your focus of vision or focal, was it? FOV. That's all I remember. Field of view. There you go. So depending on your field of view, you would see different stuff. Like if I put this cylinder right here, what you see, Vanessa, might not be the same thing that Hannah sees because your field of view might be different. So our shapes would be different depending on our focal point that we're at, basically. All right. Yeah, mine, I definitely know I went off somewhere because this is really skewed. This should have been more of a nicer rectangle. We all go with that? All right, so this next part is what you really need to know. And then when we get into lesson 26, which is today as well, it's just more practice on this topic. So this is the part you will be tested over. Not this part, but the next part. We good? Do a little art show. All right. Now you can go tell your parents that you can make 3D images become two-dimensional. All right, so in exercise 2, I'm not going to gatekeep the equation away from you. I'm just going to tell you what it is because 26 is going to do that as well, and we can go straight into that. So on exercise 2, it says, let's assume that the V1 is our projection diagram. So that's what you're looking at their origin, and the upper right vertex of the cube is located at 584. Now it's going to give us a specific point. If our screen represents a plane, and we'll call it y equals 2, use matrix multiplication to determine the vector that represents the line of sight from the observer to the projected point on the screen. So basically what we need to do, what all this means, it gives us an actual point now. So 584, it's not just a random point in space that we're trying to draw. We actually have a coordinate. And we have to project it onto the plane y equals 2. The only information you're given is 584 times some scalar t will give me something to something. All right, go ahead. Yeah, no, we're saying that we're going to take this point 584 and project it onto y equals 2. So we're going to assume that V1 is the origin. So where I'm standing is going to be the center of my universe, right? And then the corner of the object I'm looking at, we're now going to give it a name at 584, but I want it to be on this plane. So I'm looking at an object here, but I want it on the screen. So we're going to take that 0.584 and we're going to move it to the plane y equals 2. So the only information we know is that 8 needs to be multiplied by some scalar that would give me 2. But if I apply it to the y, whatever the scalar is, I have to apply it to the x and the y. So with this information, you can pretty much yes. Oh, I put it in Miss Bogner's library closet, so someone's gonna have to unlock it for you. It's but it's secured. Just find someone in the 100 office to unlock Miss Bogner's closet door. Okay, hold on. Did I answer the question or have I gotten to that? Okay. So now I can use this information to develop a equation to help me find out what this scalar would be. Now you might be able to see it and just know what it is automatically, which is perfectly fine with me. But basically this would be 8t equals 2. How would I solve for t? Divide by 8. Right? What's 2/8? 1/4. So now to get the new point that's been scaled to the plane y equals 2, I can take this 5/8, this vertex, not vertex, the vector, and I can then multiply it to 1/4. So what is 5 times 1/4? 5/4, right? What's 8 times 1/4? That would be 2. That's what we wanted. What's 4 times 1/4? 1. Very good. You could also write it like this as well if you like decimals. Doesn't matter to me. But that's it. 1.25. Good question. All right, any questions on that? So again, they really want you to go through the matrix part, really try to develop some things. I'm just going to tell you that's how you do it. Take the point, take some scalar that you don't know, and use the information that you want. If I know I want it to be on y equals 2, I at least know that part, and I can adjust my x and my z. All right, if I want it to be on x equals 1, I can go from there and go through that same process. This is what you'll be tested over. So is there questions as of right now? I have about 8 more examples. So that's what you have to do mathematically. That's what you're in charge of doing in pre-cal. Pretty much, but in a scalar sense, it does get a little bit harder in a sense that I will start rotating these figures as well, but we can still use our regular matrix that we've been using for rotations. All right, we're now going to be on lesson 26. Couldn't tell you what page. 203. So go ahead and turn to 203. And the way they write it out is they describe a set point as AT 3t, where t represents a real number. Basically, the explanation here is that you are multiplying a vector slash point in this situation by a scalar of t. So if I knew what t was, I could plug it in, and I've now scaled that point or that vector to a new location on the graph. All right? That's pretty much all we're doing. We're projecting it from one spot to a new spot. So now if you're asked to project 8,3, I'll do this again with you as well, then let you try another one on your own. I'm basically trying to figure out this 8,3, what do I have to multiply by in order to have it mapped onto x equals 1? So I basically, the only thing I know is I'm trying to make 8 become 1. So now I can develop an equation to do that. So this becomes 8t equals 1. So how do I solve for t? Divide by 8. So my scalar would be 1/8. So to figure out the answer, I can now do 8/3 times 1/8. 8 times 1/8 would be 1, which is the outcome I wanted. 3 times 1/8 would be 3/8. There's your new point. So if you had a point 8,3 and you're trying to map it onto x1, its new location would now be 1, 3/8. Make sense? Okay. Try 3. Let's see where you go with it. I do apologize for all the interruptions. Jacob, you have a question? Oh, did they say something? I just zone them out at this point. When you become a dad, it becomes really easy to do that. Now, of course, if you are already seeing the pattern of things, you don't have to write it out like I do. You can just go straight to the math. I'm good with that as well. But as your teacher, I want to show you each step of the process so you always see it. I do like an improper fraction, but I'll accept a mixed fraction. When it comes to decimals, I'll accept decimals as long as it's exact. So if the answer is like 3.14, blah, 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 I better exceed pi versus that number. Now, if it's like 1.3 repeating, I'm good with that as long as you put the line over the 3. Mhm. Did y'all already get the answer number 3? Okay. Okay. Well, I saw you talking. I didn't know. Yes, ma'am. I actually preferred that, but it really doesn't matter. No, just waiting on number 3. If you think you can do all of them, go ahead, knock it out. It's nothing different until the end.
Improper fraction is like 20 over like, right?
When the numerator is larger than the denominator, so like 20 over 4. Well, the only make difference is now what will happen is I'm going to want you to do a rotation and then scale it to a one-dimensional plane. So you'll do 2 steps basically.
8 times 5,
One more time.
8 times 5, 8.
8 times 5 eighths. Yep, and then multiply straight across. Mm-hmm. Which is?
Which is what 10.
Whoa. Do that math one more time.
8 is
Uh, correct.
10 over 2.
Okay. Which is perfect. Yeah, you went from 20 over 2 totally or 20 over 4 completely followed, and then you went 10 to 1. I was like, I don't know what happened. Perfect. All right, so we ready? All right, so once again, you're given this point 8, 3, but now you're asked for it to be projected onto x equals 5. So you're trying to find a scalar in which x will now equal 5. So we go 8t equals 5. How do I solve for t? Divide by 8. So now I get 8 thirds times 5 eighths. What's 8 times 5 eighths? 5, which is what we wanted. And then what's 3 times 5 eighths? 15 eighths. Again, if you did a mixed fraction, I'm good with 1 and 7 eighths. If you turn that into a decimal, I think that's going to be 1.875. Yep. Good. Yes. So I'm good either way. Any questions on any of that? All right. If you've already moved on, that's awesome. Let's see how far we went. Did we all move on to 4, or did we stop because it's 3 dimensions? Go ahead and move on. For the ones that didn't, go ahead and knock out 4 and 5. You're still doing the same math. You're still with 3 dimensions. This time you're trying to map on to y equals 1, and this one z equals 3. Just like we did at the exercise 2 of lesson 25, you can use that as your guide. Yes, sir. Think of fractions as division. 4 goes into 4 for one time. 8 goes into 45 times type stuff. All right, do we have 4 and 5 done, or does anyone need more time? All right. So again, you are given a point. I just find it easier to write it like this because then I can see I'm multiplying it all by some scalar. You could write it with the t on the outside of that as well. I'm wanting to project this onto the plane y equals 1, so that tells me that this 4 needs to become a 1. So I can now form an equation off of that. So 4t equals 1. How do you solve for t? Divide by 4. So t equals 1/4. Perfect. Now I can take my point, -1, 4, 5, multiply it by 1/4. What's -1 times 1/4? Perfect. And what is 4 times 1/4? And what is 5 times 1/4? Very good. And again, you could write that as 1 1/4 or 1.25. I'm good either way. Yes, ma'am? Oh, just okay. Okay. Any questions on that? Did we all finish 5? Perfect. Let's check it. Here's our point or vector, however you want to write this out as. Bless you. Again, I want to project this onto the plane z equals 3. So that tells me my z needs to be 3. So when I produce an equation, that would be -8t equals 3. How do I solve for t? Very good. So I get -3/8 as my scalar. So this now becomes 9, 5, -8 times the -3/8. What is 9 times -3/8? Perfect. What is 5 times -3/8? And what is -8 times -3/8? 3, which is what we wanted. Questions? Awesome. All right. I think that's it, right? Yes. All right. If you still have your journal, I want you to add these next 2 problems. Very specific for Tuesday. We'll go over it again, but we'll do it for here. Yes, yeah. I'll be here Monday to review. Tuesday will be a test. Yes, ma'am. It'll be our 4th test, which will be another retakeable test, but then that will give us 5 total tests. So that EOY, again, if you do bomb it, it shouldn't affect your grade much. The EOY. All right, I'm going to let you go ahead and try 1A and 1B on your own. Then we'll check it. And then I want to talk with you on number 2 because you'll see that point. There is a rotation first before there is a project. It is not. That's why I said you're going to need your workbook on this one. It's like an exit ticket. It's things that they have in there. I like some of them, and there's some I'm like, this has nothing to do with what we just did. So it's like crazy. But this one actually has more than what we did, which is what you're tested over. Yes, 1A and 1B is what we just did. So you can go ahead and do the work if you would like. You're considering to define this plane on z equals 2 for both of these points. So project both points onto the plane z equals 2, so you get 2 separate answers. This one, consider this W. Does it make sense for W to be projected onto z equals 2? And then you can answer that question however you want. And then I want to talk about 2 together.
A and B, so
A and B. Y'all can do that on your own. I'll give you time to check it. But then 2 has 2 things projecting. You have a rotation, then you're projecting, which is not covered in the notes. It's not in your book. Yeah, it's not in your book. All right, has everyone got an opportunity to do 1A and 1B? Yes. Yes. Yeah. You're still working. I'll give you more time. If you want, if you really think you understand it, you can try to. Do notice on 2, though, you have an object that's first being rotated around the z-axis. So go back about 17 lessons and remember how to apply a rotation matrix to a coordinate. Once you get that result, at what theta value is the object out of sight for the plane to be y equals 1? So what would you have to do to take that new vector that you have and turn y equals to 1? So it's like a 2-step process. Go ahead. Just put theta for now. Yeah. Usually it'll tell you like rotate 180 degrees, but this one will just put theta. That's the point, is to get a formula, really. Yeah, you won't get a number at the end of this time. On 2, you'll get a formula set up because theta wasn't given to you. No. 10 divided by 5 would be what?
2.
Yes, sir. One more time. It's just the name of the vector. It's just asking, are you able to do it? And if you are, then you should be able to explain it with your math. Or is it not doable? Are there vectors that can't be projected onto a plane? Or can anything be moved anywhere? Big question. Yeah, I think so. Yeah. I mean, even if you took the origin, that's a bunch of zeros, you could still kind of make it fall through that. Your math is good enough. Because even like on a test or something, if I asked for an explanation, you could just type the math problems out, the math work that you did. Are we ready to check 1A and B? I'll make sure everyone had an opportunity for that one. All right. So here we go. So I'm going to take X, 3, 6, and 8. I need to figure out a scalar in which I can map Z onto 2. So there is my equation right there. So 8t equals 2. What would I need to do with that? Divide by 8. I feel like we did this earlier. What's t equal? 1/4. So now I'm going to go ahead and kind of erase this t here. Plug in my 1/4. What's 3 times 1/4? 3/4 or 0.75. 6 times 1/4? 3 twos. 3 halves, very good, or 1.5. Just know on if you put 6/4, that won't be the simplified answer, and you might get that wrong. So make sure you simplify your fractions. All right, questions on that? All right, same thing with y. Take 2, -3, and 5. I need to find a scalar in which the z again equals 2. There's my formula. 5t equals 2. What do I do to solve? So the t equals 2/5. So I'm going to take that t, multiply it by 2/5, put an equal sign. 2 times 2/5, 4/5, or 0.8. -3 times 2/5 would be -6/5, or -1.2. Either way works. I'll go with that, or -1 1/5. Solid. All right. Can W be mapped onto Z equals 2? All right, let's look at it. So you got 1, 2, -1. Some scalar needs to be able to turn Z into 2. So to figure out if it's doable, let's work out the problem. -1t equals 2. Can I solve for t? Yes. I can divide by -1. So t equals -2. So therefore, I can come over here And I can now multiply by -2. So what's 1 times -2? What's 2 times -2? There you go. Was I able to map on to z equals 2? Yes, and the work there would be perfect. Can you think of a situation in which I would not be able to map a vector onto another plane? I was thinking that too, but you would still get an origin point that's part of that plane as well. So I think even the origin can be mapped on anywhere, even with a whole bunch of zeros. Maybe some imaginary numbers might not be doable. Maybe if we deal with some radicals, maybe it won't be solved. Like maybe if we would throw in a logarithm or something like that, where we have to do a square root of something that ends up being negative. Maybe that situation, that'd have to be a real advanced one though. But we're solid on number 1. Definitely a couple of questions on the test. There's 4 in total. 2 is one of them. So let's go over this. The first thing you need to be able to do is take an object and rotate it. This comes back from like prior to lesson 17. Go ahead. Oh, let's stop here then. This is going to be a process. Oh yeah. Yeah, absolutely. Well, don't need this part though.